In today's video, we're going to explore the technique known as paper chromatography. We will begin by explaining how the method is carried out, discuss the underlying scientific principles including the mobile phase and stationary phase, and finally learn how to calculate RF values, which are crucial for interpreting results. Chromatography in general is an analytical method that allows us to separate the different components of a mixture, often for the purpose of identifying what those components are. While there are many different forms of chromatography, the one you need to focus on at this level is paper chromatography, which is commonly used to separate dyes in inks and colored substances in mixtures. To begin, we first take a sheet of filter paper and draw a straight horizontal line using a pencil, not a pen, near the bottom of the paper. This line is referred to as the baseline. Next, we place a small drop of the sample ink we want to test directly onto this pencil line. This ink could contain multiple dyes, and the purpose of the test is to see how many substances are present. Now, we take a beaker and pour in a small amount of solvent, such as water or ethanol, depending on the type of ink or dye. The solvent should be added only in a shallow layer so that it does not submerge the pencil baseline or the ink spot. This is very important because if the ink spot is submerged, the dyes might dissolve straight into the solvent instead of traveling up the paper. We then place the filter paper into the beaker so that the bottom of the paper touches the solvent but the ink spot stays above the liquid level. It is also good practice to place a lid over the beaker to prevent the solvent from evaporating during the experiment. As the experiment progresses, the solvent begins to move upward through the filter paper by capillary action. As the solvent rises, it dissolves the different dyes in the ink, which are then carried along with the solvent. However, not all dyes move at the same speed. Each component travels at a different rate, depending on its solubility in the solvent and its attraction to the paper. This process separates the components, which is the main purpose of chromatography. Some dyes that are more soluble in the solvent will travel farther up the paper, whereas dyes that are less soluble or more strongly attracted to the paper will travel a shorter distance. Any substances that are not soluble at all in the chosen solvent will remain near the baseline, showing no movement. Once the solvent front, that is, the leading edge of the moving solvent, approaches the top of the paper, we remove the paper and let it dry. The resulting pattern of colored spots is known as a chromatogram. To understand why some substances travel faster or farther than others, we need to introduce two key terms, the mobile phase and the stationary phase. Despite sounding like time-based phases, these actually refer to types of materials. The mobile phase is the liquid or gas in which the molecules can move. In paper chromatography, the mobile phase is the solvent, like water or ethanol. The stationary phase, on the other hand, is the solid or thick liquid in which the molecules do not move. In our experiment, the paper acts as the stationary phase. During chromatography, each chemical in the sample moves back and forth between the mobile and stationary phases. The dye molecules dissolve in the solvent, then travel slightly, then temporarily stick to the paper, then dissolve again, and so on. This continuous exchange causes different substances to travel at different speeds, depending on how much time they spend in each phase. Substances that spend more time dissolved in the solvent, the mobile phase, travel faster and farther, while those that are more attracted to the paper, the stationary phase, move more slowly. Now, let's talk about how we can quantify these movements. Since how far a substance travels depends on both its properties and how long the experiment runs, we use a value called the RF value, or retention factor, which gives a relative measurement. The RF value is calculated using the formula RF equals distance traveled by the substance divided by distance traveled by the solvent. For example, if a pink dye moved 6 centimeters from the baseline and the solvent front moved 10 centimeters, the RF value would be 6 divided by 10, which equals 0.6. These values can then be compared to a data book to help us identify the substance. It is important to note that when performing chromatography on a pure substance, that is, a substance that contains only one compound, you will see only one spot on the chromatogram. This indicates that the substance did not separate into multiple components and is therefore likely to be pure. In this case, the RF value can still be calculated, and if matched with data, it helps confirm the identity of the substance. However, if you change the solvent or the type of paper, your chromatogram may look completely different, and the RF values will also change. This is because changing either the mobile or stationary phase alters how substances interact with the system. Therefore, when chemists look up RF values in a reference book, they must also take into account the experimental conditions, including the type of solvent and paper used. That wraps up this lesson on paper chromatography. If you found this explanation helpful, feel free to like the video and subscribe to the channel for more. Thank you for watching, and we hope to see you in the next one.